Hello and welcome back to another episode of Math with Sohn. Today, we're going to be looking at some graphs to do an energy question. So here's the scenario. We have a block that is sliding on a friction surface. And we are going to want to do several graphs. We are going to want to do the acceleration versus distance, the acceleration versus time, the velocity versus distance, the velocity versus time, and we want to do the kinetic energy compared to distance and the kinetic energy compared to time. Okay? So that's our goal. It's going to be a little bit of a struggle. All right? But we're going to get through it. So, here we go. We got, we also should include units like meters per second squared and meters, that sort of stuff. All right? So, let's think about the acceleration. Well, the sum of all forces is equal to ma. And if there's friction, we're going to have a mu times a force natural would equal ma. And the m's would cancel, which means the acceleration is just going to be mu times g. Okay, which probably means that mu is going to be some sort of negative number because it's slowing down. It's going to start fast and it's going to slow down. So that means this is actually going to be in the negative quadrant, and it's going to be some sort of negative number. Okay? So some sort of negative number, and it's going to be constant. It's going to be, let's just pretend that mu is 0.2, and that would be 0.2 of gravity, so this would be negative 2 meters per second squared, if that's the case. So we'll just pretend that it is negative 2 meters per second squared for right there. All right. So if that's the velocity as a function of distance and the velocity as a function of time, the acceleration is going to remain constant. If the whole time it's negative 2, then the whole distance it's also going to be negative 2 meters per second squared as well. Okay? So with that in mind, we need to do a velocity versus distance and a velocity versus time. And this is where it starts to get people a little confused, because for one of these, you're going to be very confident that it's, okay, well, I know that the slope of my velocity versus time graph, I know that the slope of my, I said it right. The slope of my velocity versus time graph is just going to be that acceleration. So that means that I'm going to start up here with some sort of velocity because this block was moving. So it'd be positive, and I'm going to have a slope, the slope of negative 2. Okay, good. But the distance graph is where I got a little thrown off in the beginning. So let's just pretend that we had a v initial of 20 meters per second. Let's just pretend that that's the case. There is nothing ever stopping you from tabling some things out to make it make sense. Yeah, you can use your formulas and you can do it that way. So I'm going to say that this is velocity, this is my delta x, my acceleration, and eventually I'm going to need my kinetic energy as well. And then we'll have time. Okay? So time is 0, my velocity is 20. My acceleration will be negative 2. Okay, well if that's the case, if my velocity final is equal to my velocity initial plus at, I could be like, well, velocity final is equal to velocity initial 20 plus 2 times 1. After 1 second, I'm going to have 18. Okay, so this is going to be 18. And then I could do that. Velocity final is equal to 2 times 2 times 2, and I would get 16. And I can see very quickly that it is going down at a linear rate with a slope of negative 2 because my acceleration was negative 2 this entire time, which makes sense because we already had established that as a function of time, that it went down at a linear rate. But what about the distance? Is the distance, delta x, is equal to vi times t plus 1/2 at squared? Is that also going to go down at a linear rate? So let's make sure. Delta x is equal to, what's the initial? 20. What's the time? Let's do it for 1 second. Would be 1/2 negative 2 times 1 squared. We get delta x is equal to 20 plus negative 1 times 1, which ends up equaling 19, unless I did something wrong, but I don't think I did. Okay, so now let's do delta x is equal to 20 times 2 after 2 seconds. Would be plus 1/2 of negative 2 times 2 squared. Let's see what this equals. So, okay, need a calculator. No biggie. This would be 40. All right, so we get 40 minus 4, which is 36. So how much did we go up by that time? So delta x in that first, well, 0, but then after that first second, we've gone 19 meters. After that second second, we've gone 36. So we've added 17 meters here. Okay, so let's do it again. We have delta x is equal to 20 times 3 plus 1/2 of negative 2 times 3 squared is equal to 20 times 3 plus minus 9 is going to equal 51. Okay, so what happened here? What is 51 minus 36? Is only 15. So we're at 51 here. We've only gone up, this first one we went up by 17, and this one we went up by 15. So we are slowing how quickly we are moving, which is what makes sense. In the beginning, we were moving really fast, as we had a lot of kinetic energy and a lot of velocity, but then after a given period of time, we're not going as fast. So as a function of distance, it's not going to actually work out the same way. So we have got 3 points right now. The first point is 0, 20. And then the next point was 19 and 18. And then the next point was 36. And then it was 16. So these numbers keep getting smaller and smaller and smaller the further away the distance goes. So it will end up being, I think it looks like it's going to be a little curvy. Okay, so that is a method you could use where you could just plot it out to see what would happen, and you would realize that it keeps going down. Oh man, that graph was terrible. It was 36, 16, which would have been up there. So it would have been more like that, okay, as a function of distance. All right, and it would ending up over here at some point, all right, where it would actually asymptote. It is not a 1 over x graph. It is actually an x squared graph. And we actually could have known that because we could have thought, in sense, the idea of force times distance is representing 1/2 mv final squared minus 1/2 mv initial squared, which means that distance is proportional to velocity final squared if initial squared if the final is 0. So we would have a parabola situation among us. All right. Kinetic energy as a function of distance and kinetic energy as a function of time. Kinetic energy is a function of time and distance. So force times distance represents change in energy. If force times distance represents change in energy, we have a constant negative force. And we just have distance here would equal the change in energy. So we will have a y value, a slope value, and an x value. So this is just going to be a negative sloping graph. A negative sloping graph there as a function of distance. So that one's pretty easy if you use your formulas for it. And there's normally one that's easy and one that makes you scratch your head. And that one there's no problem in just t-valuing a few things to make sure you understand it. And the slope here would equal a negative force. And that actually would have been mu times mg if we were doing this for the force of friction. Okay. Kinetic energy as a function of time. Well, kinetic energy, when we were doing the t-table as a function of time, it would be 1/2 mv squared. So let's just pretend that the mass is 1. If the mass is 1 and our velocity was 20, this would be 1/2. Actually, it'd be easier if our mass is 2. 1/2 2 times 20 squared, which would be, we'll put it over here, kinetic energy. 1/2 2 times 20 squared is 400. Then we would do 1/2 2 times 18 squared. 18 squared is 324. Then we would do 1/2 2 times 16 squared. So it'd be 16 squared because 1/2 of 2 is 1. 16 squared is 256. What are these dropping by, and is it quadratic? And the answer to that is yes, it is quadratic. Okay, it's going to keep going down by a x squared value. So that means as a function of time that this would be parabolic And then what would end up happening, it would end up going this way if this force was able to get it to turn around. So this part would not be included in the answer, but it would stop here. You could think of it as, imagine it would be parabolic and quadratic and go the opposite direction. Let's say you were having a box go this direction, and if you were pushing with a force in the opposite direction, you would slow it down, and then you could speed it up in the opposite direction. So kinetic energy as a function of time would be parabolic. It would have a minimum value, and it would look like that. Okay? All that being said, there's a few other pointers that I would like to give you. They're pretty obvious. If you have a force versus distance graph, the area represents the change in energy. So that would mean that 1/2 force times distance, if it's a triangle, would equal 1/2 mv final squared minus 1/2 mv initial squared. And there are many other things that you could do for graphs. Always never take them for Graphit. A joke to end the day. Until next time, stay positive, my friends, and I will see y'all later. Bye.